Net ionic equations. And I promised you 2 challenge problems for the start of today's class. So we'll do these 2 challenge problems and then we'll get into some acid-base chemistry. Bless you. Bless you, bless you. Whew. Alright, so that's one, and the other one is Alright, so here's my challenge question. My hint is that they do not form solids. So it is an ionic equation, but does not make a solid. So you'll probably have to think about what are the ions that make this thing up, and then how do you recombine them. All right, so let's think about this first one. What 2 ions does sodium hydroxide break up into? Hint, one is sodium. Okay. And what's the charge on a sodium? +1, okay. And then what about this guy? What's its charge? -1, yep. Okay, how does this break up? What 2 ions do I make out of this? An H+, and then what's left over? This NO3, right? All right, so looking at that, who is going to recombine? The sodium's going to go with what guy? This guy, this NO3. Do I have to do anything to charge balance those? -1 +1, okay. I'll leave it state of matter empty. All right, what happens when I combine an H+ and a hydroxide? I make water. What state of matter is water? It's a liquid. Sodium nitrate, solid or aqueous? It's a nitrate, aqueous all the time. Let me do this one. Abigail, then.
I was going to ask you between aqueous and...
Oh, so aqueous means it is a solute in a solvent. Liquid means it's a pure molecule. Is that your question too? Perfect. All right, so this right here, right, that is my molecular equation. All right, so then what do I call this kind of equation that shows all the ions? Just regular old ionic. Who are the spectator ions now? Who shows up on both sides of my error? I'm assuming everybody in their head's like, must be sodium and nitrate. Those are spectator ions? Yeah. So then my net ionic equation all right, so why don't you guys work on the second one. I'll tell you it's very extremely pretty much exactly like the just one we just did.
What is the charge supposed to be up there?
This?
On the ionic part at the end?
No charge. That's an L. It's a little liquid. Something sticky on the bench. All right, what two things does this break up into? Best guesses. Yep, an H plus. And then this guy you saw a lot of in lab this week. This is the acetate ion. Right, so acetic acid, acetate ion. All right, the calcium would have what charge in this molecule? +2. And then what about this? It's -1, but how many of them do I have? 2, right? So, what will be one compound that gets made in this reaction? Water. We're going to make water. And the other one must be Ca acetate ion. But would those be charge balanced if I put a calcium with an acetate ion? It wouldn't be. So how do I fix that, right? The Ca has a +2 and the acetate's only -1. What do I need to double? 2 acetates. Sarah, question?
Wouldn't you have, if you combine the H and OH together, wouldn't you have H3O and there be 3 H's?
One of these with an OH minus?
With 2 OH minus.
Oh, I'm going to make 2 waters. I wasn't balanced. I wasn't done balancing, sorry. Right, because we have 2 of those, so if I have 2 of these, I have to have 2 of those. So it's kind of a back and forth, figuring out what you make, and then balancing it, and then balancing the big molecules. Yeah, so I got 2 of those, 2 of those, 2 of those. Yep. Ran out of space. Okay. So then I have 2 of these, 2 of those. All right, so now I have my molecular and ionic. Who are the spectator ions in my ionic equation? Which ions appear on both sides of the arrow? The calcium appears on both sides, yeah. And there's one more. The acetate ion. So my final net ionic would be that. How do I simplify that? Divide everything by 2, right? All right, that's as tricky as they come. So what is different about these ones versus the ones we were doing on Friday? What's the biggest difference? Right, before we're making solid, now we're making a liquid, right? We're making water. Specifically, we're making water, both times. These are acid-base reactions, where I had sodium hydroxide, which is a base, and nitric acid. Down here, I had acetic acid and calcium hydroxide, so I had acid-base, acid-base. So now we're ready to do acid-base reactions. All right, so we're going to use, there's 2 different ways we can define what an acid and base is. We're going to use the Bronsted definition. The other one's the Lewis definition, so if you're reading your textbook, they describe them both, but we're just going to use the Bronsted definition. The Bronsted definition of an acid says that it is a molecule that donates a proton. What kind of atom is a proton? Does anyone know? it's a hydrogen, specifically it's an H plus. Right? Because think about it, right? If I had hydrogen, how many protons does it have? This guy. How many protons does hydrogen have? 1. How many electrons? Has 1 electron, 1 proton, but how many neutrons? If its mass is 1 and it has 1 proton, 0 electrons. But it's neutral, right? So it has to have an electron and a proton. But if it loses the electron, what is left? Just a proton. So H plus is literally a proton, just hanging out, doing stuff. Chemistry, doing very important chemistry. But H plus means I could write this the same as that guy, right? Like we were way back in chapter 7, 8. It's just a proton. All right, so an acid is something that's able to donate a proton, and a base is something that is willing to accept a proton. So let's look at some examples of reactions and see how an acid, Abigail, yeah.
Wait, why did you put the H plus with the proton accept? Is it a accept? Isn't it the H?
I'm just saying a proton is this.
Oh, okay.
That's all. I'm just rewriting it. H plus is a proton.
Okay.
And so a base is able to accept an H plus. And an acid gives away an H plus. All right, so acids. So here I have hydrochloric acid. And water. All right, so if this is hydrochloric acid, it's looking to donate a proton. There's only one other thing in this reaction. So water is going to accept the proton. So hydrochloric acid is acting like an acid. So what is water acting as if it's accepting? It is a base. So for every acid-base reaction, you must have one of each on the reactant side. You have to have one acid plus one base. All right, so if hydrochloric acid is going to give away its proton to water, we make this new snazzy form of water. This is called that's a D, hydronium ion. And then we just have chloride. We have the hydronium ion and the chloride ion. All right, if I tell you the hydrochloric acid is a strong acid, what does it tell you about what kind of electrolyte it is? Strong, weak, or have no idea? If you flip back in your notes to Monday, a strong electrolyte is also a strong acid. They are the same thing. So a strong acid is a strong electrolyte. Hydrochloric acid is a strong acid, which means hydrochloric acid is a strong electrolyte. So how much does it dissociate? 100% or just a little? 100%. Yep. So a strong acid so it completely dissociates. What is this kind of arrow telling you about how much it makes products? All the way, completely makes products. Right? So if it's completely dissociating, it means it's going to, all the H's are going to break apart from the Cl's, which means we're going to make a lot of this, which is an acid. Strong acid makes lots of acid. Okay. Let's do another one. All right, here I have sulfuric acid. And if again, I tell you sulfuric acid is a strong acid, what kind of electrolyte is it? Also strong. So sulfuric acid is a strong acid, which is a strong electrolyte. So how much does it dissociate? 100% or you don't know? 100%. So what is my arrow showing you? Completely, right? It's only one direction. So let's look at a case where it's not quite so obvious. All right, so I have sulfuric acid, right? It has 2 protons. This first step gave away 1 proton, and now I have HSO4 minus. That guy can give away another proton, right? Make the sulfate ion. That's perfectly reasonable. What is this arrow showing you, though? Is it completely in one direction, or am I showing both directions? Okay, I'm showing both directions. So based on the fact that I'm showing both directions, does it completely dissociate? No. All right, so if it does not completely dissociate, is this a strong electrolyte or a weak electrolyte? This now is a weak electrolyte. If it's a weak electrolyte, is a weak base or a strong, or weak acid or a strong acid? It's also a weak acid. So our acids are going to fall into 2 categories, strong acids and weak acids. And strong acids completely dissociate, they're strong electrolytes. And weak acids don't completely dissociate, right? They're weak electrolytes. That'll help us make some predictions about products. All right, so then let's do the same thing looking at bases. All right, so bases are proton acceptors. So over here I had the hydronium ion. The hydronium ion is characteristic of what happens with an acid. Bases they often make hydroxide ions in solution. And hydroxide, right, is this one. OH minus. So if I have a strong base, what kind of electrolyte is that, strong or weak? Right, strong electrolyte. So if I have a strong electrolyte that's going to completely ionize to make these hydroxide ions, what does sodium hydroxide then break up into? Sodium hydroxide. Right, something like that. If I have this calcium hydroxide. This right here So this production of these hydroxide ions are characteristics of strong bases in solution. So when I looked at the acids on the previous page, I made hydroniums in water. That means I have an acid. These guys making hydroxides means that it's a base. Especially a strong base, makes lots of those. There are some other trickier bases, right? These are all strong that they completely dissociate, which means I also have weak bases, which are weak electrolytes. And they ionize only partially. Oh, I forgot my L on water. All right, so I have, does anyone know what this guy is? Ammonia. Ammonia is a weak base. So if it is a weak base, bases accept protons. So if it's accepting a proton, where's the proton coming from? The water. So what would be one of the products I would make? If water's going to give up a proton, what does it leave it with? Hydroxide. And then what happens to this? The N stays the same and still H's. Now how many H's would I have? 4. And if I give it an H plus, what's its new charge? Plus. So acid-base reactions are very similar to the ionic ones we just did. But instead of changing around all the ions, we're just going to move a proton from one reactant to the other reactant. So the protons just move from side to side. Before I leave this slide, if this is acting as the weak base, what is the water acting as? It is an acid, right? Because it's donating a proton. Question?
So you said that the presence of the OH means that it's a strong base?
No, production of lots, the only thing it makes is hydroxide, right? Because sodium hydroxide is just going to break into sodium hydroxide. This made a sodium hydroxide and this other ion.
Oh, okay. Gotcha.
And then I also have these double arrows that I kind of wrote over. Yeah. So what is the double arrow telling me about how much it ionizes? All right, makes a little bit. Does a little bit forward and a little bit back. There's like a sticky spot right here that I keep sticking my hand in. Ugh. All right, questions about the introduction to acids and bases. Those are like just basic kind of definitions. This is also in your book, Common Acids and Bases. So here's my recommendation. There are 6 strong acids and 3 strong bases. If you know those 9 things, those are the only strong ones out there. So if you don't recognize it as a strong acid or a strong base, it must be weak. So we are going to we talk about the strong acids quite a bit. I mean, acetic acid is usually my go-to weak acid. Just love that guy. Sometimes we talk about some of these other ones. And there's only one weak base we will ever talk about, ammonia, like we just did. So you probably don't need to memorize these because we're going to use them so much that you'll know them. But I guess write down specifically there are 6 strong acids and 3 strong bases that you need to be familiar with. And because you know naming things, you should be able to recognize them if I write it out in words or letters, back and forth. All right, so let's talk about how acids and bases react together. All right, the first category of acid-base reaction is something called neutralization. The name will make sense here in about 2 minutes. Okay, neutralization occurs between a strong acid and a strong base. So you have to have a strong acid and a strong base reacting together. What is the direction of the arrow telling me about its ionization potential? Completely ionizes, right? 100%. So I have HCl and I have sodium hydroxide. We want to predict what products will be made. Knowing that we're going to make a salt and water, what is one of the products that I should write down? I should write down H2O. All right, so did the hydrochloric acid or the sodium hydroxide donate a proton? Right, this guy donated a proton. Since it's an acid, it means it's a proton donor. Whoop. So if this is acting like the acid, what is this acting like? Base. So if it is a base, is it accepting or donating a proton? It's accepting. So this went off with that to make water, so what is left to produce? Salt, specifically. That guy, right? Sodium hydroxide, or sodium chloride. Yeah, there we go.
Why isn't the salt smaller than water?
Because using our solubility rules, we know that sodium chloride is always soluble. So acid-base reactions require some of the solubility rules as well as the, it's just, this whole chapter like builds on itself and builds and builds and builds. All right, let's do one more of these. What if I make bless you. All right, potassium hydroxide and nitric acid. Looking at our previous sheet, and the fact that we're still on neutralization, these should both be strong. Not trying to trick you. So if they're both strong, should I have double arrows or a single arrow? Single direction. All right, is the potassium hydroxide or the nitric acid acting like the base? Which one's the base? Number 1 or number 2? 1 or 2? Number 1 is the base. So what does that tell me about this? Has to be the acid. All right, so if this is the base and it's going to accept a proton, what is one of the products it's going to make? Water. So what is left to make? A salt. What am I going to call that salt? Potassium nitrate. How do I feel about that? Good? Fairly confident? Justin?
Oh, never mind.
Oh, okay. All right. I'm going to stop there. I'll do weak acids and bases. And then we'll do some titrations on Monday. Practice titrations. I want to make sure you have enough time to do your quiz.